pattern recognition.
Pattern recognition.
Music is just a series of altered patterns. The musician creates the pattern and makes us anticipate resolution, and holds back, makes you wait for it. There's patterns in everything and everyone.
Patterns.
You're listening to God Roll Partners.
Good evening, folks. Can everybody hear me? And is it loud enough or quiet enough over the top of the background music, which I hope you can hear as well? By 5. So yeah, am I good? Hey Peleus, we can hear your voice. Please turn it down. I hate you. Good to go. Awesome. Okay, I'm going to minimize this stuff over to the side. Okay. All right. So from what I can tell, I am currently streaming to all three. From what I can see, it is coming through, and I don't have the volume up, but I'm pretty sure it's working. The YouTube one does look a little bit on the blurry side, and I think that could have something to do with Restream. Mixer looks okay, and I think Twitch looks okay as well. The music can be a bit quieter. Okay, I'll reduce the volume again. How about that? Is that better, Jay? Because I want it to sort of be there just as a nice sort of rhythm behind the scenes. There we go. Okay, fantastic. Greetings to everyone, regardless of which platform you may be joining me on. Thank you for tuning in. If you have any problems with the technology, then please sing out straight away. because I would hate for someone to miss out. Triple audio stream is on all 3 platforms. Awesome. Okay, well, I'll leave that running, and hopefully I won't break anything in the process. So let's move on, and I'll assume everything's fine unless you guys have issues, and I'll assume that you guys are gonna whinge at me. All right, so let me flick over to this scene. Now, you'll probably notice, I don't know whether you can see the mouse, but somewhere over here, because when you're streaming, I can't see everything, but I think around this area, there should be the little chat window, which is putting all of the chat messages from the 3 platforms in the one spot. So I've put that little thing there so that you can see, and in the hope that like I can actually see it there, but still have it disappear without interfering with what's on screen. But I'm going to do that because when I see chats appear in the window, I'm going to try and address them as I can, so that the people who are watching the video know what it is that I'm talking about. No IPv6. Yeah, I can't honestly say that I've even considered IPv6 related stuff. So, Mark Gibbons, YouTube too blurry. I really think that's a restream issue. I'm really not sure what I can do about that. Let me have a quick look to see if there is a setting that I can tweak, and I apologize for that. But yeah, it does look really blurry, doesn't it? Let me see if I can fix that in some way. Just bear with me for a minute, sorry. And while I'm playing with said settings, I'll just continue talking. So this is going to be a follow-up stream from a few days ago. Okay, let's have a look. It says here, stream health is currently okay. So we've got 5 people currently watching on YouTube, and ooh, how did that? It looks like it's kind of kicking in and out. Hey, gear icon and upstream quality manually. Yeah, can you guys change your stream settings to 1080p manually, and tell me if that solves the problem. Like, lock it to 1080p forcefully and see if that actually looks better. I noticed that on the archive and the text was small. Yeah, auto seems to be being buggy. Yeah, I think so too. Zarubus mocking the Mo. Yes, well, not really. This is just because I'm so pasty white, any little bit of growth really looks like I have a Mo, but I don't actually have a Mo. I'm just lazy. Hey Justin, thanks for coming in, dude. And thanks for dropping by, even if you need to bail out very quickly. So yeah, the people who are sitting on YouTube right now, can you please manually change your settings to high def and leave it like that, and tell me if that's that resolves the problem for you. And if it doesn't, then maybe for now jump to another platform. As crap as that is. Okay, Mark, that's great. That does work for you too. Cool. All right, I'm going to do my best to answer your comments and questions as quick as possible. Now, you should be able to hear Guy Baroni in the background. As always, I really like having his stuff playing in the background because it's kind of chill, kind of relaxing. This is my first time watching. Will you do a CTF? Sahil, what I'm going to be doing is I'm going to be finishing off the process of exploiting a CTF challenge that I started in the previous stream. So if you look at the video archive, so the most recent video prior to this one is the lead up to where we are now. So if you're not interested in spoilers, you don't necessarily want things to be ruined for you, maybe put this one on ice and come back and watch this one after you've watched the previous one. But basically, I'm just going to follow up from where I left off. Like, my virtual machine that you can see on screen right now is in exactly the same state as it was when we stopped. So there is a little bit of prerequisite knowledge expected, but what I'll do is I'll give a really brief recap of what it was that we did and how we got here. So the challenge that we were taking on was this one here, this Tokyo Western's CTF from 2016. A challenge called Diary, which was a 64-bit Linux binary. And I'm Going to catch up with part 1. Okay, thanks, mate. Much appreciated. So basically the story with this binary was it was a diary sort of logging application where you can specify a date, you can specify the size of a diary entry, and then you can punch in some text into that diary entry. And what we found, even though I didn't find it until very late, was that it had a custom allocator which allocated memory in a big block of memory marked read, write, and executable, which again I didn't determine, pardon me, until the end. And also noticed at the end that seccomp is in play, so they clearly have manipulated the permissions of the process, probably in a way that's going to make it very hard to actually get a fully interactive shell working with this thing. So where we left off was we had come up with a way to add and remove diary entries in such a way that would allow us to dump a valid heap pointer from memory, which we could then use later on to attack the custom heap management facilities, linking and unlinking of a free list specifically. And with that, we were able to exploit a write what where vulnerability, overwrite an entry in the GOT, and from there we could point code execution directly at our area on the heap because we were able to leak that heap pointer. And as we can see, this is exactly where we got to here. So this debugger is still running from the previous stream just about 2 days ago. And we can see that code execution has stopped at this first breakpoint, which is what it is that we had put in memory in the first place. OJ, very new question. Can you expand on what the GOT stands for? Yes. The GOT stands for the Global Offset Table. So in Linux, the way that sort of dynamic linking and whatnot works, like the GOT is kind of similar to the import address table, I guess, in Windows land. So you have an entry that says, I need to call a function in libc, or I need to call a function in LD or something else. And so you have the global offset table, and then you have something called the PLT, which is the program linkage table, I think. And so what happens is the GOT points to the PLT, and when you first invoke the function for the very first time, the GOT entry which points to the PLT redirects execution to the PLT. The PLT then goes away and looks up the address of the function in the library that it depends on, and when it's done, it takes the address of that function and writes it back to the GOT. So then the next time the function is called through the GOT, it just goes straight to the resolved function. So the PLT is about sort of on the fly figuring out the addresses and wiring them into the GOT as you go. There you go, procedure linkage table. Thank you, Peleus. I thought it was program linkage table, but clearly not. Procedure linkage table. So yeah, so you've got the GOT, which is like the IAT. You got the PLT, which is used to dynamically figure out addresses, and when it's figured those addresses out, they're rewritten back to the GOT. I think that's how it works. There are other people on the stream who are probably more knowledgeable in that than me, but that is my understanding. There you go. Peleus is answering those questions for me as well. So I think this little chat thing is quite good. But let me know if you find this chat little window annoying, if it obscures view or anything like that. It's kind of hard to find a place to put it on screen to keep people aware of the context without it sort of taking up an enormous amount of space. Okay, so where we left off. Oh, by the way, failed to mention tea. Always have tea. Hacking without tea is very uncivilized. Tonight's tea is a fairly strong rooibos. I'm trying to avoid the caffeine for the evening. About 2 inches directly up would be good. Look, seriously, Peleus, I know you love looking at my face. Don't pretend that you don't. Smashery. Oh, have you got whiskey? Maybe next time I should do a stream with some whiskey. I know Cooper would appreciate that. Our good friend Whiskey Sec. And just like last time, I've got some dark chocolate. Dark chocolate and tea go very well together. Highly recommended. This is only 85% though. Last time it was 90%. So as long as it's sort of 85 to 90, if not higher, you're in a good spot because it's not too sweet. Okay, so where were we? You think the messages might be hiding too quickly on that window. Also, with the length of some people's names, one person can fill up. I agree. I'll probably change the timeout or the fading away of those messages to maybe last a little bit longer next time. But I think fading them away after a period of time is wise. Maybe I think it's currently set to maybe 10 seconds. Maybe I can set it to 20 or 30 seconds. I'm kind of scared of making the box any bigger because I think that if the box is bigger, it'll just take up too much of that right-hand pane. I may even need to like dedicate a whole separate pane to it. So anyway, let's bear with it for now and we'll see how we go. And I will definitely take your feedback on board. Thanks, Wolf, and same with you, Zarubis. And maybe I can tweak that for the next stream. Make it maybe completely over to the right so that we can always see it. Oh, you'll do it for me. Thanks, Lurker. That's awesome. Yeah, I'll punch my creds in directly on stream so that, you know, if anybody else wants to give it a go as well, then they can. No problem whatsoever. Okay, so let's just have a quick recap of the code that we've got here. This first block here, what we were doing is we were creating 3 diary entries, all separated by a year. And we just basically filled them up to all but one of the last entries. And the reason for that is because the new line character was actually overwriting 1 extra byte. Remember in our analysis with Binary Ninja or IDA, we were able to see that there was an extra byte being read beyond how big the buffer was that was allocated. So we're avoiding that at the start here. And then once we've done that, we create 3 and then we delete the last 2. Then we go and create another one which is big enough to overlap the first and the second, and we fill up that information, fill up that diary entry with enough characters to go right up to the edge of a heap pointer, and then we print that value out. And then once we printed that value out, we can read the whole value in off the screen and chop off, you know, just the characters that we're actually interested in and unpack that into a heap pointer. And that's what we were able to do. Like, we can actually see that. Hang on, let me just go back up. Oops. Go back up here. So the shellcode pointer would be at this. So we figured out a heap pointer, and you can see here we had a very simple calculation that told us where our shellcode pointer would be with respect to the heap pointer that we leaked. And that's what we can see here. So we basically used this as a pointer later on in our payload in our write what where. So from there, what we do is we create, I think, did we create another? No, we didn't. Yes, we did. Yes, we did. We created 2 more entries, and then we wrote to the first one. Oh, no, we deleted. That's right. We deleted, didn't we? No, we created one, and then we deleted it after mucking around with the very last byte. Actually, that's one thing that we can do as part of this analysis. More comments? No. As part of this analysis, maybe what we can do is try to make sure we fully understand how that write what where came about, because there's probably something missing. But at the end of the day, it could be something as simple as a size parameter has been overwritten to something bigger than it should be, and hence, you know, we're able to move a pointer to a different location or something similar to that. So from there, we use our write what where, and we write the value of the heap pointer to the GOT. So you can see, where are we? We are writing here. Here we go. We are writing to the GOT the shellcode pointer. That's basically what's going on there. And then later on, when we free, we end up in this scenario where our when we exit the program, the exit function in the GOT is executed, and because that pointer points to our area in the heap, which is read write X, we're able to execute our own shellcode. So what I'm going to do is just quickly show you the virtual memory map. So this is the area of memory that's allocated for the sort of internal memory management functionality. As you can see, it is read, write, and execute. So that's a sure sign that bad things are going to happen, right? And this is where our code currently sits. So that's pretty useful. And based on what we've got going on up here, we can see that RIP currently points to our first block of CCs, our int3s, debug breakpoints. hex CC is the hexadecimal opcode for int3, and int3 is software breakpoint. And so the debugger will latch when it sees int3 and say, hey, we've hit a breakpoint. Extra chocolate. So good. I know, it must be disgusting having to listen to me chew through chocolate while I'm talking. It's very bad manners. So, I'm just going to go back to our Windows 10 box for a sec, because I want to have another look at Binary Ninja. We're going to have a look at seccomp, and the reason why we want to do that is we know that seccomp is in play, and that's going to be mucking with the permissions or the feature set of syscalls that we're actually able to invoke. Is that a Linux thing? No, that's not just Linux, that's Windows. I don't know about other architectures, but I'm sure there is an equivalent. I don't know whether the opcode is exactly the same across all architectures, but for x86 and x64, hex CC is the int3 opcode. Okay. Okay, time for me to type a password in, but that's okay because it's on stream and you guys are all totes legit and trustworthy, right? I don't have to worry about that. Not at all. All right, so let's quickly go back to this init function. I'm going to go back to the disassembly graph because I like looking at the graphs. So init looks like this. No worries, Jay, not a problem at all, mate. So the init function goes and does a bunch of stuff. So this setBuff stuff looks fairly typical. It's calling setBuff with both standard in and standard out and passing 0 in. It's effectively saying don't use input or output buffering. That's all that's doing. Init heap, we don't really need to look into. This is just allocating a massive block of memory that's read-write executable. Here we can see this line where EDX is being set to 7. We are saying we want to mark this memory as read-write executable, and then we invoke mmap with those parameters. And then there's effectively some accounting, some metadata for the custom allocator happening, going on there. And then we go to init seccomp. How are you finding Binger versus IDA? I wouldn't say that I'm using one over the other as part of my daily analysis. I'm actually using the two side by side. So I've got IDA open here as well. And I do that because sometimes I find the features of IDA are just a little bit more powerful, or it might be better at analyzing a particular area of code than Binger. But I probably don't need to say that. The general workflow of moving around Binger and the look of it, I mean, it's much easier on the eye and it feels much better to use than IDA. So I kind of use this for my initial analysis, and if I butt up against something that annoys me, then I'll duck over to IDA and then I'll come back here. But I find this much nicer to use. So that's effectively the reason why. So yeah, there you go. So according to this, what we're doing here is we're invoking PRCTL, or what looks to be twice. So for those people who don't know what PRCTL is, let's open a browser here. I don't think I've done anything dodgy on this machine that I should be embarrassed about as far as history is concerned. So PRCTL is a function. Let's just we'll open a few and see. Okay, so this performs operations on a process. It's called with the first argument describing what to do. The further arguments can be significant depending on the first one. So basically what this function allows us to do is change the capabilities that are present in the current process, right? So if we have a look here, sorry, back to here, we pass in 1, 2, 3, 4, 5 parameters, and these last few will probably vary depending on what the first one's specified as, okay? So rather than going through every possible case, we're just going to have a look at what it is that's specified in this case, all right? So the first argument in 64-bit on Linux goes in RDI, I think. We did go on that last stream. RDI, which here you can see EDI is being set to hex 26. So what we need to know is what does hex 26 map to. So I'm going to cheat, and I'm going to take this value and I'm going to type in define this, and somewhere hopefully there will be a header file that documents what this is. Okay, so here we go. And the value we were looking at is hex 26. What's hex 26? In decimal, it's 32 plus 6, isn't it? It's 38, is that right? So 38 says PR set no new privs. All right, so let's go back to here. Let's see what this says. So what we're here is we're saying set the callings thread no new privs bit to the value in arg2. With no new privs set to 1, execve promises not to grant privileges to do anything that could not have been done without execve2. For example, rendering the set user ID and set group ID bit modes and file capability is non-functional. When set, this bit can't be unset. So we're turning something off and it can't be turned back on again. Okay, the bit is inherited by fork and preserved across execve2. All right, so that seems to be part of one call. If we have a look here, we can see that ESI is set to 1. So that basically means with that set to 1, execve2 promises not to grant privileges. Okay, so we're disabling the ability for future execve calls to grant privileges, right? So that's what this appears to be doing. Prevent execve from granting privs. Oops, can't type. So we'll just document that for now because that may be useful later. Now here we're doing it again. You can see we're calling PRCTL again, and this time we're passing in hex 16, which is 22. So let's see what's mapped to 22 in here, if anything. 15, 34, 32. Oops. Find 22. Oop. There we go. Set seccomp. Okay, so this is the magic one. This is where other things are really going to start mucking with us. Okay, so set the secure computing. So that's what they mean by seccomp. I love the languages in these documents. It promises not to do things. Yeah, I know. You gotta love it, don't you? So here we're basically mucking with the secure computing features that are baked into Linux. So what we're saying here is we are toggling we're turning things off. We're basically saying we're not going to let you do anything interesting. Now the second parameter here is interesting too, because it basically says what you can and can't do. So here we're setting ESI to 2, right? So according to this, seccomp mode strict, I wonder if that's defined in this header file as well. Nope. Let's go define this and find out where this is. Seccomp defs. So seccomp mode filter. Okay, so we're specifying our own filter, which basically means a set of rules that would allow that indicate what can and can't be done. So I'll go back to here. With arg2 set to seccomp mode strict, which it isn't, so we'll skip this section. arg2 set to seccomp mode filter, which it is. The system calls allowed are defined by a pointer to a Berkeley packet filter struct passed in argument 3. This argument is a pointer to a struct sock fprog. I have no idea what that looks like. Let's go have a look. Struct sock fprog. Okay, so We have an unsigned short that says how many of these blocks, and then we've got one of these sock filters for each block. So let's go and have a look at what the code is doing here. And we're passing in this. So I would assume, so this is the pointer to the seccomp, sorry, the sock fprog, right? So that's probably what I'm going to change. What I'm going to do here is specify, I just want to make sure that that's what we're talking about. Yeah, unsigned short, so it's moving word, that's a short. So var 8, sorry, A8 is probably going to be var A8. Yeah, okay, so this is our, what did it, sorry, what's it called again? Sock fprog. Alrighty. That's what I think's going on. We're definitely passing that in here, right? Because RDX needs to point to that thing. So the address of that is what's going into RDX. Now we need to just figure out what the structure of this thing is going to be. So let's have a look and see what kind of values are actually being written to this thing, because we need this unsigned short value. Where is that being written here? Move dword RVP minus blah. So what that's saying is there's going to be 12, hex 12, is that right? If that's true, that means that there are hex 12, or I should say 18 decimal instances of this sock filter, okay? And the sock filter, maybe the sock filters are in this data value here. It certainly would look like it, wouldn't it? Because, here we go, what do we got here? Check this out. There's a bunch of information here leading right up to here. That looks like a hard-coded set of data with very similar values. So for each one of these, what have we actually got? I don't even know what these things contain. Let's go back to the thing that defines it. So filter code, a jump value, I don't know what jump true or jump false, generic multi-use field. And so the filter codes, what do they mean? If anyone already knows a fair bit about the, a while ago I made a bare minimum seccomp filter example to experiment with it. Fantastic, let's copy that link. And we'll open that up in stream. Thank you, John. Let's just have a quick look at what this seccomp thing does. Okay, right, so what do we got here? Yeah, gotcha, allow. Righto, so here we're basically saying what you can and can't allow, and these are the names of the syscalls that you are allowed to or not allowed to do. So, so according to this, John, your stuff's really helpful, mate. Thank you. You're basically disabling all of this stuff. You're disabling mmap, xxve, brk, access, open, fstat, close, read, blah blah blah. So I would probably assume that if this here is the block of sort of seccomp stuff. This block of data represents like a filter or a net that a syscall is run through, and if it falls out the other end as okay, then the syscall is allowed, and if not, it's not allowed. So I think it's probably fair to say that based on the fact that this piece of code here says there is, oh okay, that's it, awesome, thanks John. Given there are so many of them, what we're actually doing here is see this rep movsq keyword, we're copying this data into this memory location. So that's just dropping it onto the stack, right? Cool, thanks very much, John. Appreciate your feedback, mate. I will we'll hopefully see you for the next one. Have a good sleep. Don't have to worry about hacking and viruses. I use a Mac. Such a troll. Okay, so I'm not going to go through every single one of these entries, but clearly this is a full table of what they are. And they're looking pretty similar, and they're all, how big are they? They are, let's go back over here again. 16, 32, two blocks of 32 bits. So it's basically a 64-bit value. Am I reading that correctly? 16, yeah. So that's all that is. And assuming that this is the first one, C0. That's in 64T. Okay, so that would be 200000. So all these would be zeros. So that plus that. Yeah, okay, I see. So basically look at this value here as a 64-bit chunk up to here. So between here, and then from here and here. But the important thing I think for us to note is, so the first thing here is the filter code, which is the first 4. Hang on, what am I talking about? 1, 2, 3, 4. It's a 64-bit value, right? So that's 2, 3, 4. That's 32. That's 64. Okay. So there are 1, 2, 3, 4. 4 times 1, 2, 3, 4, 16 with the extra 2. So there you go. Yeah, that's where they are. So this is definitely the block of filters. So if I assume, given that I would assume that one of these says both of these bytes being 0 mean don't allow it to happen. And there's a buttload of zeros in all of these. I'm going to go ahead and say that for the most part they can't happen. And given that this is a CTF challenge, I'm going to go ahead and say that you're not allowed to do whatever it is that it's disabling. Now I think just for the sake of shizzles and giggles, we should just generate some shellcode and see if we can run it. So a classic shellcode would be 64-bit. Let's just go ahead and we'll create like a execute bin sh using the standard approach. Let's shove that shellcode in our payload buffer and see if it works. Pretty certain that it's not going to. But I'm going to use MSF Venom for this. So MSF Venom payload, we'll go Linux x64 exec cmd equals bin sh. That's pretty much all we need to worry about as far as that's concerned, but we need to specify bad characters because remember we can't specify new line as a bad character, as a character, because that will cause the truncation of the input in memory. So let's go format Python. Pardon me. Assuming that I know what I'm doing. As you can see, it's pretty quick. Alrighty, so we're allowed nulls and things like that, as we've already seen. It was really only new lines that could muck with us. So I'm going to take a copy of that, and let's just drop this in. Where are we? I'll drop it in here for now. Alright. Comment payload equals. Basically, it's the same as execve bin sh. That's basically what we're looking at there. Now, what we should probably do is make sure that the code that we're passing in isn't going to get clobbered by anything. So, how many bytes did we say that's going to be? That is 47 bytes. So let's just have a look at where we are, like with EIP. We know that EIP is currently pointed to the heap here. So if we go x47bx that address, check this. check this out. So clearly we are overriding, which doesn't actually surprise me because we're using the unlinking and linking of the free list to muck with stuff. So while we're able to pass control directly to the area of the heap that we control, the first, what looks to be 1, 2, 3, 4, 5, 6, 7, 8, 16 bytes, we just need to jump over. So instead of SC pointer, let's skip the first 16 bytes and go to the next block, which is immediately after the stuff that we're clearly clobbering. And then from there, we know that we can put our shellcode in at that location, and hopefully from there we'll be okay. So let's have, I don't know, let's go 100 BX. There you go, look at that, there's plenty of space after that. Okay, so we'll do that instead. Let's quit out of that, cancel, and rerun it, see what it does. Did that do what we were hoping? It doesn't look like it, does it? Maybe we went a little bit too far. 100 BX. So this is basically where we landed, right? We didn't go far enough. Did you actually send the buffer? Yes, so it's already in here. We're basically saying that we want to point execution past it, right? So we should basically be saying when we exit, we're not going to the shellcode pointer, the start of the shellcode block. We are going hex 10 beyond it, which should take us past 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So for some reason that didn't do what I was expecting. I'm wondering actually, this is interesting. Let's undo that and do it again. Because, and what I should do instead of hard coding addresses, I should be able to go x 100 bx rip -1. Okay, so we are definitely landing 16 bytes before. Yeah. Now what I want to do is run this again and make sure that the offsets are still the same. Right, they are definitely still the same. Is it just overriding whatever is 8 bytes past where you land? I think so. Yes, that's exactly what I'm thinking. So instead of changing this, we need to leave that as is, and probably just hard code a jump, like a short jump in here. So what I'm going to do is tools, exploit. I'm going to use Metasm shell. I think it's x86 underscore x86 underscore 64. I wish I could just type x64 there, that'd be good. Window is now behind your head. Oh yeah, sorry. My bad. There you go. Thanks for that, Atwolf. So we're just kicking off Metasm shell. Now what I want to be able to do is jump a small distance relative to the current location. Now I can't remember whether this includes the jump call or not. I'm pretty sure it does. So let's just say we jump forward 8. That looks legit. So let's go jump forward 16. So that's the code that we want to put right at the start of our shellcode, right? So let's take this and come back over here. Now, shellcode is going here. So we want to go our jump is that. And we want to throw the jump in plus that minus the length of the jump to make sure that our stuff is still correct, right? Now, actually what I'm thinking of doing, instead of doing it this way, let's have a payload buffer. Payload plus equals, I'm gonna start with a breakpoint because I like to see where it lands. Then I'm gonna add the jump. Okay, we'll add the jump to be consistent. We'll use single quotes. And then I'm gonna go payload plus equals whatever it is that we're going to add as a padding. So I'm gonna continue with breakpoints times whatever the length of the thing is that we're gonna send, which is 1FF. Minus the length of whatever the payload happens to be, and then we'll send line payload. So yeah, Ash, I think you were bang on there, mate. Oops. Okay, so seeing trap. So our current, yeah, that worked perfectly. So if we just quickly look at the bytes, we landed on our hex CC, and then we're jumping forward a certain amount. So obviously we're not jumping far enough, because this will land in D1. Oh no, we are far enough. So I need to reduce the jump by 1. So instead of 0E, I need to go 0D. Because I've got this byte in here, which is the breakpoint. And that will put us directly after the buffer that we're looking to abuse, I think. Is that right? No. Isn't this interesting? So Rex plus 8 is... Oh, it's because we've got a null pointer in... Is that just by chance? Yeah, it is. So this is a problem because every now and then we'll get a null pointer in a heap address. At that point, when we're dumping our heap address out, we won't get the exact area where the heap address is. So that's what happened before. We ended up with a heap address that had a null byte in the middle of it, and we were only able to read the first however many bytes and not all of the bytes. That was pretty cool, hey? Someone's pinging me on Signal. Who is it? Nobody. Nobody of consequence. Everyone enjoying their chocolate and tea? Okay. So, as we can see, our jump will land us now at C1D0. C1D0 is immediately after the address that we're looking to land in, which is exactly what we want, right? So if we skip over, that's where we are. Now we can start dropping our shellcode in. So here I'm going to go payload plus equals buff, which is our execve shellcode. Make sure that we save that. We will quit out of this and let's go again. Oh, here we go. We've got another null byte in a heap address, I think. RDX. See how short the... Oh, hang on, maybe we don't. Clearly, Rax... Oh, Rax is pointing nowhere useful. So if we look at what our heap address is at the moment, VM map, have a look at these. There you go, there it is there. There's a null byte there. See that? That's a heap address with a null byte in it. So we managed to score yet another heap address with a null byte in it, and that's what's caused us problems. So rather than try and fix that, I'm just going to rerun it. Okay, so what have we got here? We have landed exactly where we had hoped to land for our breakpoint. Okay, and you know what else I'm going to do? I'm going to just clear this up a little bit again by putting another breakpoint directly in front, so that we can see that it's nice and clear. Okay, so there's the hex CC, followed by, so our jump points to 91D0, which is here. Now, where's our hex CC byte? See, I'm not seeing it. I would expect to see, oh, I did that, that was stupid. Actually, no, that wasn't stupid. That's exactly what I was expecting. Oh, I know what our problem is, right? So we've got this jump, but we need to basically pad that jump with crap, right? We've got 2 bytes, and we need to pad out 16. So I'm just going to put A in here times 14, because 14 plus these 2 bytes is 16, which means that our CC should now appear here. So this byte will appear in this location. You're a fan of payload. Yeah, I was thinking of doing the same thing, but I kind of like sort of seeing everything separated in separate steps, and the plus equals is nice and consistent for me, Smash. But yeah, you effectively got exactly the same thing, right? You're right. The L-just is cleaner. Okay, so have we got to where I want to be this time? No. I've gone 1 character too far. Ah, yes, because we've got this extra CC. So that should be 13. So all of these bytes here need to add up to 16 in length in total. So maybe what I should do is go, let's use Ash's suggestion. L-just, we want to go 16 in total, and we're just going to fill it with A's, right? And then here we'll do the same thing, but this time we'll go OX1FF, and we're going to fill this with breakpoints. Make sure you remove the plus equals. Yes, yes, I hear you. Thank you. So that's the first section, second section. Okay, so yeah, I'm making that mistake far too many times myself. But yeah, thanks for that. That's super helpful. Okay, now it's looking a little bit better. Okay, let's quickly look at the contents of the stack. So there's our first CC, which is here. That's what we've just broken on. Here's our jump, which should skip over all of this nonsense and land at 71D0, and you can see that it is landing at 71D0. So we SI, and we're finally here. Now, the rest of the payload, pardon me, should be however many bytes. It is 47 bytes, right? So from here, this one here, 47 bytes ending at OF05. 0F05. Okay, so this should actually be a valid execve payload, right? And I'm just going to continue. And what do we got here? We've got a sig trap. So something's not happy. Let's just have a look at what we're looking at. Oh, sorry, sig trap. That's a breakpoint. What a fool. Let's run it again. Look at that. Program terminated with the signal SIGSYS bad system call. So clearly we've hit a system call that we are not allowed to invoke, and I'm assuming that's execve. Clearly it's execve. If you're going to make this challenge interesting, you've got to block execve as the system call. So we may be in a position to go and try and do something like open a new file handle and try and read a file off disk. Maybe that was the intent of the original challenge. I seem to remember something in the documentation that said you're allowed to invoke /bash or something like that. Not really sure why, but we're looking for shells, right? We want actual shells. We don't just want to read files from disk. So, what are we going to do? What are we going to do? What options do we have? Is there a way to easily convert that block of memory with all the filter restrictions into a readable list? That's a good question. I'm going to go with probably, but I'm not really sure I want to go and parse that, because clearly execve is blocked, and regardless of what else is blocked, I'm interested in getting a fully interactive shell. So that probably means that I'm going to have to execve, which means we need to somehow bypass seccomp. Now, in the past, I admit that every time I've come up against a challenge that has seccomp and restricts syscalls, I go ahead and do something with other syscalls, including things like opening files, reading files, etc., that kind of stuff, and then dumping flags to screen and moving on. But we're not actually part of a CTF right now. We're just abusing the challenge. Did you check what's blocked? Sin, no, I didn't check what's blocked, and that's effectively what @wolf is asking. Should we go through and check what's blocked? We can do that. We already know for sure that execve has been blocked, so not that hard. Just write a custom elf loader into memory. I'm going to take that as a troll. A troll. I wouldn't know how to do that. Certainly not within this stream. So what I'm thinking of doing is coming up with some way of bypassing seccomp. So let's assume that a significant portion of the syscalls have been limited. Sin, you're saying seccomp tools might help. Okay, seccomp tools. Let's find out what seccomp tools is. Can't link it. It's on GitHub. No problem. Seccomp tools. Let's see if that comes up. Here we go. What do we got here? See, this is what I love about live streaming and having full interactivity. We get all kinds of people mixing in and having conversation, and it's really, really good. So I'm learning at the same time, which is fantastic, right? So this project is targeted but not limited to analyze seccomp sandboxes, CTF bone challenges. Some features might be CTF specific. Okay. Available on Ruby gems. Well, it just so happens that we have a Ruby installation in our in my Metasploit setup, so I'm going to use that here. There we go. Does that mean I can just use it directly? Seccomp tools -- help. Seccomp tools help. Ah, beautiful. Seccomp BPF disassemble, automatically dump. Okay, so let's have another look at the documentation here. So dump the seccomp BPF from an execution file. This work is done by the pre-trace syscall. Beware of the execution file be executed. Yeah, we don't care about that. So we basically just call dump and pass it in. Okay, fantastic. So we'll go dump and we'll pass in stream. I think it's diary. Look at that. Sin, you are a legend, my friend. That is fantastic. Pipes. The example doc is for this. You're joking. The same binary. Nah. It is too. That's hilarious. Well spotted. It is for the exact same binary. That's insane. Who would have thought? This isn't awkward at all, is it? That's really cool. Thanks, Sin. That's really handy, man. I'm going to be making good use of that in future. So it looks like we're not allowed to open at, execve, clone, fork, vfork, create, etc. That's really good. That's exactly what I was thinking needed to exist. I'm glad that it does. So am I. So if I had swag to give out, Sin, you'd be getting it, my friend. That's really, really cool. I realize that most of you are watching this on Twitch. Sin is commenting directly via YouTube, so hopefully you're seeing his comments appear on stream, despite the fact that he's on a different platform. So fantastic that you're here helping out in that manner, mate. That's really cool. All right, so exec VE, exec VE out, create, vfork, fork, open at, and open. So those things, not possible. Okay, so what are we going to do to give ourselves a full shell? How are we going to bypass? How are we going to bypass this? What are the options? I admit that on Tuesday night when we finished up, this problem sort of appeared in my head, and I hadn't done this analysis. I just thought I'm going to assume that most of the things are turned off, and that we're not allowed to use them, with possibly a couple of interesting exceptions. So I had been pondering the kind of thing that that we could possibly consider. Now, does anyone else out there have any ideas? I mean, I was thinking we could do some Googling, like bypass seccomp, and just see what comes up. Collection of shellcodes that use strict system rules make sandboxing. Bypasses are not possible because seccomp is flawed, but because sometimes seccomp filters are inappropriately configured. Just like an exploit takes advantage of programming mistakes, these bypasses take advantage of configuration mistakes. Okay, so typical exploit scenarios, you have a vulnerable lap in which you can inject shellcode. The sandbox, you need to tailor shellcode to the system calls that are allowed. Yep, that makes perfect sense. So this is what we usually do. We want to read files from the file system. Read again, remotely read a file. Okay, so this isn't really talking to us about anything that's useful. So it uses open, which we're not allowed to use. Open again, which we're not allowed to use. Open. Okay, so none of these are particularly useful to us because they all require open. POC for bypassing sloppy seccomp black. Now that is interesting, isn't it? Heaven's Gate. Sin, you did that challenge, so it kind of be a spoiler. Oh, okay. Well, I will appreciate you not telling us. But this, I'll admit, this piece of information here is exactly what I was thinking about. So, for those who don't know, and I'm pretty sure that everyone here does already know, I've done a fair bit of work on Meterpreter, and particularly Windows Meterpreter. And one of the things that Meterpreter has the ability to do is migrate itself and or inject code to and from 32 and 64-bit processors. Yeah, I know, Atwolf, really. So the interesting thing here for me was this is when I was first exposed to Heaven's Gate on Windows. And Heaven's Gate is like in fact, I don't even know where the term came from, but I first heard it as Heaven's Gate. And Heaven's Gate refers to transitioning of a thread in Windows from 32-bit mode to 64-bit mode. Now, you don't really have to worry about this in any other scenario except for when you're trying to invoke a create thread call from a 32-bit process into a 64-bit process. So if you call create remote thread and you're 32-bit and you try and create remote thread in a process to 64-bit, it won't work. So what you have to do is you have to transition your current thread into 64-bit mode, then call create remote thread. And then when that's done, transition yourself back into 32-bit mode and off you go. So on Tuesday night, in fact, it probably wasn't Tuesday night, it was Wednesday morning when I'd been chewing over this, I was wondering whether or not seccomp was something that applied to the architecture, and if there was a possibility of moving from one architecture to another, does that then mean that system calls, the filters on the system calls no longer work? So this Google search and this thing has pretty much validated that, and Sin has just mentioned that 32/64-bit is a hint. Okay, so the easy way of doing this at this point, I would say, is like if this is indeed the path, then we could read this code here and cheat. But I would like to maybe avoid doing this and do it ourselves. So I'm going to assume that what we want to do is transition from 64-bit mode in our current thread back to 32-bit, and then execute 32-bit shellcode, which may give us a shell. Thoughts? I'm pretty certain that this is going to not only be fruitful, but it'll be a fun exercise. And for those people who have never done anything with transitioning from 32 to 64-bit mode or vice versa, then hopefully this will be an educational exercise for you as well. So that's the path I'm going to go down, even if it is, even if there are nicer / easier ways of doing it. Hey Swappage, how you going, mate? Sin CS register, yeah. So what I'm going to do is use the method that I'm familiar with, and that is when you transition from 64-bit to 32-bit, or from 32-bit to 64-bit, you're basically doing a far return. So instead of like in a standard return, the value at the top of the stack is popped into RIP or EIP. In a far return, I think it pops 2 values off the stack, and one of them goes into the code segment register, and then ret's called on what's left. So it pops 2 values. Heaven's Gate, Windows, knocking on Heaven's Gate. Let's see what this is. So this is the stuff I'm more familiar with in Windows land. Here you go, Heaven's Gate dynamic processor mode switching. So let's just have a look at what this is doing. There's probably going to be a code example here that will tell us. Is there these are all images, that's unfortunate. Heaven's Gate, control flow guard, not worried about that right now. Oh, that's one thing we're probably going to have to consider. Greetings, is that Wormair? Catching your stream online almost felt like we... Thank you, sir. I appreciate your commentary. So what's going on here is we've just landed ourselves in a situation where we've got code execution on a 64-bit binary, and we've got a seccomp filter that's preventing us from doing things like execve and open. So we want to be able to create a scenario where we can get a fully interactive shell despite the fact that there's a seccomp filter in place blocking execve calls. So what I'd like to be able to do is bypass that by transitioning from 64-bit into a 32-bit mode and executing 32-bit shellcode in an effort to bypass the seccomp filter, which hopefully will only apply to 64-bit code. That's basically where we're at. But what I'm looking for is something that's just going to give us a quick assembly code example. Heaven's Gate. Okay, what do we got here? Oh, this is this code looks familiar. I've looked at this before while doing interpreter related stuff. x64 enter says exit. What does this puppy here do? Exit CS, so call +5, move blah, ret F. Here we go, okay. So check this out. This little block of code here, enter CS. And this is a topic I'm so interested, I can't follow along work hours. Yeah, no worries, Swappage, all good, mate. So clearly, what's going on here, what are we doing? We are entering 64-bit long mode. So call +5, add dword esp5, ret F. I would have thought that we needed to put, yeah, okay. So you push a, what is it, a value, you push a value on the stack that says what the CS register, the code segment register, needs to have in it. Then you push the address that you want to return to and you call ret F. So the values that we need to put in, I think one of them's 32 and the other one's 23. from memory, and I might be wrong. Let's have a look. 23 and 33. Okay. I thought it was 32. Am I wrong? Honestly thought it was 32. Heaven's Gate. Let's have a look in here. X64 call. What does X64 call do? That'll be in .h. Mem copy C. I don't care about any of that. Don't care about any of that. X64 call. Let's just see what it's doing. Red F. So it is 33. Yeah, okay. So 30. For some reason, I thought it was 32. I thought it was going mad for a minute there. So in order for us to transition into 32-bit mode, we basically need a pointer to where the 32-bit shellcode is going to be, and we need the value 23 to go back from 64 into 32, right? According to this hex 23. Okay, so we want to go back into 32-bit mode, which is hex 23. So we put that on the stack, and then we put the return address on the stack, and off we go. So we know where we are on the heap. What issues are we going to face here? Because if we're going into 32-bit mode, we can't use 64-bit pointers, right? Okay, so that's a problem. If we are looking to return control in 32-bit mode, we can't have a 64-bit address. We can't be anywhere in 64-bit land and currently executing, and we can't have any pointers to shellcode that are in a 64-bit address either. That's a bit of an issue. Oh yeah, I can't do this anymore, don't I? I've got to run this again. That seccomp tools thing was so good, Sin. Thanks for that. That really did open the door for us, didn't it? Okay, so what are we going to do? What are we going to do? Because all of these addresses are clearly 64-bit. They're not going to be helpful for us at all. And with ASLR, we can't really pick up where... Look, we're going to have to... Maybe what we're going to have to do is put some shellcode in memory that we then copy to this location. What do you think? If we took some 32-bit shellcode and we copied it to this location, then did the far return, but we would need to mark this as executable. Bugger. Okay, if we're going to mark something as executable, we need to be able to invoke the mprotect syscall, right? So was that blacklisted? Open annex clone 4v4 create x. Okay, so we can still invoke the mprotect syscall. X64 syscall mprotect. Actually, system call table for X64. Here we go. Sys mprotect. Where are you? 10. Oh, you're kidding. 10. 10 is hex 0A, which is a new line. How cute. All right, so to invoke mprotect, we need to... What do we need to do? Isn't that typical? That's just typical. There's like a nice little FU. Just a little, here's another little step that you got to go through. So here's what I'm thinking of doing, right? We're going to, first of all, I'm just going to mark this area of memory here as read-write executable through an mprotect call. I'm then going to copy a block of shellcode to that location, and then we're going to do a far return to that location. And hopefully that means we'll transition back into a 32-bit mode and we'll be able to invoke our execve. How do you guys feel about that? Does that seem legit to you? See this new line, throws it away. That's what you, yeah, exactly. Exactly, that's just bloody typical. All right, so that just means that if we are going to do an mprotect, we're going to do an mprotect call. Hang on, we've got to stay in this. I'm all over the place in my virtual machines, aren't I? We're just going to have to set up our shellcode so that we're not passing. We'll have to just say set something to 10 and then increment it. Sorry, 9 and increment it by 1. So if I'm understanding it, the seccomp filters are per architecture. Yeah, that's what I'm thinking. I'm thinking that that's the case. And the reason I'm thinking that is because of the Googling I did before. Yep. So, all right, let's start writing some code. So we know that this 64-bit payload is not going to do anything for us, so let's get rid of that. So that's where we're putting our shellcode in, right? So I'm going to leave this stuff in here because I think that's important, but I'm going to set that to a NOP. In fact, I can just get rid of that now, and we'll just use the jump straight away, and we'll start putting our shellcode in here. Now, the first thing that I want to do is what is it that I want to do? We want to do the mprotect call, don't we? Mprotect. So that means we need racks to be set to 10. Of course we do. There's Metasm shell. So if we go mov racks, what do we got there? No, let's not do that. Let's go, yeah, let's do that. And then we'll go mov al. Okay, so we can't do that. What can we do? Maybe we can do this. Or racks -1. And then we can add racks hex 11. So basically, if we all racks with -1, then we should be setting the entire content of the racks register to FFFFF. And if we add 11, then that sets the value to 10. And we end up with 10 in the register without having an invalid byte. Does that seem legit? So let's shove that back in over here. Just for shizzles, and we'll see if that actually works. Righto. So I'm going to run that just because I want to see if it's doing what I would like it to do. Did I not? Needs more NOPs. Shut up, multi. Just stop it, bro. Okay, so this is interesting because clearly I've mucked something up over here. Oh yeah, I know what I've mucked up. I'm gonna need to leave that as a NOP because of the jump. /x90. You're actually technically correct, which is the best kind of correct multi, but in that case, there we go. That makes more sense, doesn't it? So here we don't know what racks is going to be, so we OR it with FFFF, and then we add 11, and we end up with racks set to 10. Oh no, hex 10 is not what we're looking for, is it? We've gone hex 11. It's not hex that we need, it's just 11, which is OD. That's what I wanted. That's better. So there we go. We have got a new line in racks without having it being clobbered. Nothing but a lurker. Do you like 80% choc Tim Tams? To be honest, no. I still find them really sugary. I did a Tim Tam slammer with Brian over during the Spectre Ops training earlier this year. That was really good. But holy moly, the Tim Tams are sugary, man. I don't know how much I can deal with them. Yeah, that was good fun. If you guys don't know Brian, you need to. He is a top lad. Top lad. Alrighty. So what else do we need to do? We need to, once we've set that, unsigned long start. So we need to put the address of the area of memory that we're going to change into RDI. So what is that address again? We're going to poke it in here. Alrighty, so mov RDI. I'm just going to do this really cheaply because I'm lazy. So we move that into RDI. We want to move what goes into RSI. Sorry, RSI needs the length. How big is that area of memory? 2 and 3. It's only one page, so we'll just do the one page thing. Mov RSI. Then what else do we need to do? When I went over the US, I bought my friends every type of Tim Tam I could get, and they were gone in like 20 minutes. Yeah, they do love them over there, don't they? Hey. Size length prot. Now we want read write X, which is 7. Yeah, so that needs to go in RDX. Right. So where are we? Now, actually, at this point, what's in the RDX? Yeah, it's a full pointer, so we're gonna have to clear it out. Okay, so if we went, where are we? Mov RDX 7. If we did XOR RDX, and then add or mov DL 7, is that smaller? Oh, it's smaller by 2 bytes. Let's do that. Now I know that a lot of this stuff can be done in Pwn Tools, but part of the reason why I'm doing this is because I want to see for myself that we're not going to get a new line character appear. And yeah, I guess I could spit that out as part of our output with Pwn Tools, but I'm just making sure of it myself first. All right, so let's just make sure that we've got everything in place there. What have I done? I should add it to the payload, shouldn't I? That Metasm shell is really cool. Need to check it out. Yeah, Sin, this is a savior for me, dude. I'm so used to using it for Metasploit related stuff. So if you pass in this -A x86 x64, that'll give you the 64-bit version. And if you don't specify the architecture by default, you'll get the 32-bit version, which we'll be using in just a minute anyway. Actually, no, we probably won't, because once I've got 32-bit shellcode, I won't really care about doing it all manually. I'm just going to use execve and say that I've basically doing exactly the same as what I did up here, but with, where is it, 64-bit MSV. So get rid of this, and instead of 64, we'll go x86. So this is what I will want to do. Jesus, quick, isn't it? Come on, spit it out. So there you go, 70 bytes, a bit bigger than the 64-bit version, hey? So that's what we will use once we actually get into 64-bit land. Pardon me. Oh. I've just had another aha moment. Mr. Destructor Hack is actually very cool to use the Pwn Tools ASM. Yeah, I absolutely agree. And I really do need to get more familiar with it because I know it does a bunch of magic stuff and we can actually have our assembly code in line. But I do like to be able to just do a quick scan and make sure that there's no bad characters. And I do like the sort of feedback loop. The only thing that's crap is that I have to copy and paste into my payload. Maybe we can tidy it up. So at the end, when we know that we've got everything in here that we want, we can just throw it, like tidy up our exploit to use the pwntool stuff instead. We'll probably do that. Okay, I'm pretty sure that the pwntool stuff has bad character stuff baked into it as well. But yeah. Yeah, simple as that, right? Okay, so with that in line, the first, we need to actually do a syscall thing. So given that we've come this far, let's just syscall. I like to leave the comments in line in here as well, so that we can see what they map to. Okay, let's give this a go and just see what it says. Oh, no, don't do that. Exploit. All right, so we set racks to -1 and then add 11, so we get 10. We set a pointer to RDI. We set RDI to the pointer that we want to change. RSI is the length. We clear out RDX, set it to 7, and then get ready to syscall. So let's have a look. VM map at the moment. We know that this area of memory is read-write. Hey, look at that. That's a winner, isn't it? Happy with that. All right, so we've clearly been able to modify memory. Obviously, the syscall works, so you know, seccomp hasn't blocked that, as we found with our analysis earlier on, that syscall hasn't been disabled. So now we've got an area of memory that we can really muck with. So what I'm going to do now, this one thing that I thought about just before that I failed to mention. Have a look at this. So I assume that before we ret, we're going to have to change our stack pointer to point in that area as well, because ESP is not 64-bit. So we're going to have to not only copy some code over, we're going to have to put the code in the same area, and we're going to have to put ESP or RSP pointing to an area just above it, so that when we do the ret, everything's fine. And that's not a problem. Like we can do some math leading up to that anyway. So what I'm going to do is I'm going to split things. I'm going to split things pretty much in half, and I'm going to make it so that we write to an area of memory the 32-bit shellcode, right? And just above that shellcode, is it above? Yeah, above that shellcode in memory, we're going to write like a fake stack. So we'll write hex 23, followed by an address that points to the shellcode, and we'll probably have to have a gap in there as well, so that ESP doesn't point to the exact same location that shellcode's in. So maybe like have a buffer of 32 bits. So basically what I'm saying is the stack will end up looking something like, the area of memory will end up looking something like this. We're going to have ret address. We're going to have, I think it's immediately above that, isn't it? We want to go CS, which is set to hex 23, followed by the return address. I think it's that way around. And then 4 bytes of junk, JUNK, followed by shellcode. Okay, and then the ret address is something that's basically going to point like down to here, right? Does that make sense? Oops. So the return address is going to point down to where the shellcode is, because we know where this is because it's going to be somewhere in the middle of this memory map. We'll just put it like 6 to 800 or something like that. So it's in the middle. So there's space above for things to push stuff onto the stack and whatnot, and the shellcode will go below. I think that makes a lot of sense. So what we actually need is this. We need to go so shellcode. Any questions? So we're going to have a 32-bit value. So this will pwn.pack 32-bit. That's going to be hex 23, right? Then we're going to pack 0x00602. I'm just going to put it bang in the middle, like that, because that's where the shellcode's going to go. And then what are we going to do? We're just going to pad it with some crap because I don't want ESP to be pointing to the same location. So let's just go p320. So we'll just leave it as null. And then immediately after that, we're going to have whatever the buffer is. If you can get a chance, please scroll up and show what libs you're importing in Sploit. Yeah, for sure, for sure. So all I've got at the moment is pwntools and sys, and I'm not even using sys just yet. I was going to use sys to pass values in, but that's just a default that I kind of include when I'm writing stuff. But for now, at the moment, the only thing we need is pwntools, okay? Which is pretty cool. Alrighty, so where are we at? So we've got the buffer there. So shellcode now has to have the buff appended on the end. All right, now the buffer is this stuff here that we know is the 32-bit version of execve. Okay, x86 version of execve with binsh. Okay, so that's basically what we're looking to add, yeah. Righto, so we've got a syscall in place. We've converted, what have we done here? So let's put a little comment in here that says mark area of memory as RWX. Mark, actually we should say 32-bit area of memory as RWX. That's what that's doing. I'm just going to move this up here so that it's out of the way. I'm actually going to do that here as well, and we'll leave the payload at the end. Okay, so that's basically this shellcode. Even though it's probably not the best name, we should say. I'll leave it as shellcode, and I'll rename it in just a minute. So what we need to do now is we need to copy the 32-bit stuff to the 32-bit memory region. Okay. Now we know that the amount of data that we're going to be copying is the length of the shellcode. Okay, and I'm going to be using, is it rep movsb? Is that what it is? Rep movsb. I think that's what it is. Movsb. I've said movsb. SB sign byte. Move a byte. Move a byte. So this is basically what we want to do. We set the value in ECX or RCX to the number of bytes we want copied. We point ESI at the source. we point RDI at the source and RDI at the destination, and we call rep movsb. And it says move the byte from ESI to EDI ECX times. Okay, so that's what we want to do. We are going to go back to Metasm shell. So here, what we're going to do, we might want to change RSP to, yes, that's exactly what I was talking about before. And I'm going to do exactly that, but I'm going to do it in one step. So we'll get to that though, Sin. That's exactly what I was talking about before, and I know that's a point of pain for us at the moment. Anyway, what I'm going to do is we're going to mov into RDI. Now we need to know the exact address, which is going to be 0x6. Hang on, what was it? 6, whatever this address is, minus, so that's what's going to be there. We've got 1, 2, 3 lots of 4 bytes. No, that's okay. Don't apologize, man. You hit a really key point. And that's exactly what we need to do. So I'm glad you brought it up. 1, 2, 3. So there's 12 bytes here backwards. So it's whatever this is minus hex 12, right? Minus OXC. Okay. So that means that RDI is going to point to the exact location that we want. Now that address is what we're also going to be setting RSP to before we do a retf. Okay. In fact, we can probably do that straight away. If we put that in RSP instead, then we can just copy that value, mov RDI RSP. We're basically going to say, right, we're pointing the stack at our sort of fake stack frame. And then we're going to move EDI there. And now we're going to copy this fake stack frame and our shellcode in one big hit. We've got a mov RCX, whatever the length of our shellcode is. I need to know what that is. Now, I don't like hard coding stuff, but for the sake of this discussion, that's exactly what I'm going to do. Print len. Oh, actually, you know what? We can probably do better than this. But anyway. 82 bytes. Okay, well that's fine. Because we might be able to just squeeze it in. Mov RCX 82. Let's do it the shellcode golf way again. RCX mov CL 82. Oh, it's not hex, is it? It's just, oh god, I can't type tonight. There you go, saved 2 bytes again. So let's take this out and shove that in our exploit. Copy of 30-bit stuff in memory region. So here, that is preparing for the copy. Now we need the source. So before we do this, we actually need to include a call that goes to where? We basically need to get whatever the current pointer is, whatever the current rip pointer is, but we can do that with fairly basic math, right? Yeah, okay, we'll come back to that in just a sec. But basically what I want to do is we need to point ESI, RSI, to the shellcode that we're looking to execute. So we need to put that in memory somewhere. But for now, we'll assume that it's somewhere else. Isn't this a medium level challenge? This seems rather complicated for medium. Or are you just making it difficult on yourself trying to get a shell? That's a good question. I don't know. I think as far as the level of difficulty of the challenge is concerned, that's kind of down to interpretation. I wouldn't necessarily say that this is super hard. I mean, particularly with the ability to type in bypass seccomp and the third result say, oh, you know, if you flick between modes, then you're onto a winner. The rest for me isn't that tricky because I'm very familiar with flicking between modes. Now it's just a matter of just going through the process. Now we could probably go through this a fair bit quicker, but the purpose of the stream obviously is to go through this into a bit of detail in the hope that people are going to learn from it. So yeah, I don't know. If you think it's hard, then it's hard. I wouldn't say it's easy. I'd say there are elements that are easy and elements that are hard. But yeah, it's your call, man. If you feel that, then I'm not going to disagree with you. I don't think it's a trivial challenge. There is a little bit involved. So yeah, pace has been perfect. Awesome, thanks, Slick. That's really nice to hear. Okay, so where are we at? That's right, so we need our shellcode in here, right? So what I need to do, somewhere in here we need to place the shellcode. Right. So I'm going to put it at the moment, I'm going to put it after. Actually, what I should probably do is put it right at the start. Let's do it here. Okay, and then I'm going to go payload plus equals. Now we need to actually put in a call that skips over the shellcode, right? I'm going to put another breakpoint here just to use as a delimiter so we can see how far we're going. And this will make sense in just a minute. So let's go back to Metasm shell. We're going to go call plus however long it is. Don't you already have a jump just up? Yeah, I know, but I want the call, not the jump. I don't want to jump, I want to call. And the reason I want to call is because when I do a call, then RSP will have the address and we can just move that into ESI. Yeah? So that will be plus, it's probably going to be 82, right? Because that's the length of the shellcode. Call plus 82. Now that's pretty messy, and it's bigger than it probably needs to be, but that's exactly what I'm going to do. So call plus 82. I'm just going to do that. Oops. Sorry. Does that make sense? Hey, OJ, happy to watch you. Thank you. Thank you very much. Thanks for coming, Manuel. It's good to have you on stream, dude. Much appreciated. Let's hope I don't run out of space. Yes, I absolutely agree, but I don't think I'm going to run out of space. I think we've got plenty. So if that is this here is, what is this? 82 minus 1, 2, 3, 4, 5. I reckon that's probably what that is. So at this point here, this hex CC, what I think is going to happen is that the address that's at the top of the stack should point directly to shellcode. So what I will look to do afterwards is mov from whatever RSP is into RSI. Yeah? Do I need to put, oops, do I need to put keyword to make sure that it's, no. Yeah, so it's just mov RSI RSP. So we're just going to copy whatever the pointer is straight out of memory, and we should be good. So let's put that here. And see what this does. Okay. Okay, so what do we got? So we've got our breakpoint, which is what we've just hit here. So the call is going to take us to this address here. Now let's watch what's on the stack. Okay, so we should have a pointer that points to 6D1D6. So if we have a quick look at, we go X just 10BX rip, E8 4D0000 is where the call instruction is, which is exactly what this thing here is. Immediately following that is 2300, sorry, hang on, where is it? Shellcode. Ah, here we go. So yes, 23. That's our 32-bit value for 23, followed by, let's do a few more bytes. Let's make it 20 instead. So, where are we? There's 23. There's our packed address. There's our full null bytes, and then DAC3BB, which is DAC3BB. So it looks like we've got exactly what it is that we're looking for. Okay, so let's go and execute the call. Now at the top, we are directly pointing at the 23, which is exactly what we want. Yeah, I think. So we've gone to the wrong location though, because, hang on a sec, yeah, because RIP is in the wrong spot. RIP is at 223 and we actually want RIP to be at CC. So where is the CC? Let's do that. 10BX at RIP. Okay, so 1, 2, 3, 4, 5. We need to add 1, 2, 3, 4, 5. Okay, so this needs to be a 7. So if we can go, oops. 40 plus, so let's just go back over here and we'll do it in Metasm shell to make sure we don't get it wrong. 52. So that needs to be 52. Let's try that again. Call, boom, there we go. So we're bang on the int3 now. That's more like it. Okay. So at this point, the top of the stack here points to the right location. So then when we do the move, RSI now points to where we need it to be. So then we should be able to go and do, now RSI can be left alone. But you see the good thing is that we don't even need to mark the area of memory as RWX yet. We can actually do the copy first because it's already read-write. Yeah? So we move RSP, change the stack pointer, copy it to RDI. We do the adjustment of RCX, and then we should be able to do the rep movsb. So this should do the full copy of that many bytes to the target location. Is this making sense? Cool. Righto, RSI now points to the source. RSP points to somewhere pleasant. Copy that to RDI, XOR, 52, rep NZ, movs byte pointer. Okay, so if we go X, and we know that it's how many bytes? 87 bytes? Was it 87 or 82? No, it was 82 bytes. BX. To which address? RSI. It is RDI, isn't it? Okay, so that's basically where we're writing to. So if we skip over that. I can't remember how to go over this without cranking it 87 times. So what I'm going to do is cheat. Oops. Someone else knows a nice way of doing that, and they should let me know. Okay, look at the stack. Stack pointer has got all of this stuff in it. Sweet. So there's our 32-bit packed value for 23, which is our code segment register. There's the address that we're going to, which is 2800. There's this, which is a padding, and there's the beginning of our shellcode. So if we can go X, we just want to make sure that the shellcode at the given location is correct. So we'll just, I don't know, look at the first 10 bytes at 0x006.02800. Is that right? Oops, that's a C, not a 2. DAC3BB4E, DAC3BB4E, sweet. Okay, so we've now copied, which is pretty cool. You could just read the shellcode straight into that. Read, oh yeah, that's true. Read is not blocked. That's a good point. So we could actually throw it down the wire immediately, yeah? Ah, well, we'll just do it all in one foul swoop instead of doing another one. Yeah, that's a good idea. But, you know, I'm doing it slightly differently. Yeah. I hadn't pondered that because read hadn't been blocked, but I just assumed at this point that we weren't able to do anything else, so I'm just throwing it all down the neck in one go. So instead, yeah, we're just going to copy it and off we go. All right, so where are we going to next? That's right, we're setting up our syscall. So at this point, if everything is going as planned, we should literally be able to call retf because we've already set up our stack accordingly, right? Okay. How's that looking? No? Well, let's watch and see what happens. Okay, so skip over this breakpoint again. You may have the CS and EAP around the wrong way for a retf. Yeah, I think you might be right, actually. But for some reason I was thinking it pops the code segment first. But let's have a look. Let's consult the documentation. Oops. retf. Let's see. Pop the instruction pointer only. Well, retf will pop both the instruction pointer and the code segment. Yeah, so you might be right. What does retf stand for? Nope. Come on. retf transfers control. Far pops the IP followed by CS. Okay, so yeah, it is the other way around. Bugger. It'd be exactly the same, I would assume. The interesting thing is, does the code segment value need to be 32-bit at this point? Doco says, when executing a file return, the processor pops the return instruction pointer from the top of the stack in the EIP, then pops the segment register from the top. That actually makes a lot more sense. Actually, no, it doesn't make more sense. So the reason why I thought popping the segment register would make sense first is because at that point it knows how to align itself. It needs to know whether the code segment, I guess that's a fixed size anyway, isn't it? It's 32-bit. Okay then, well let's just let's just adjust our approach. So our shellcode won't have 23 followed by the address, it'll have the address followed by 23. All right, let's do the call. Got our breakpoint. I can probably get rid of that breakpoint now. Do the copy. We'll do our cheeky skip over so that we don't have to watch it all. So RSP now contains all of the stuff that we're expecting. Do our syscall and retf. Sigsegv, what does that do? It's clearly not happy. Okay, I wonder why. I wonder what it is about that that's bad. I mean, do we have to do anything else? Like, do we have to clear out existing registers? Don't know. Oh, someone on Mixer is also hosting. That's fantastic. Instead of B star, can you U star? Good question. I assume that's some GDB magic that I know nothing about. So this rex.w retf, I'm not so sure about. Maybe this is the problem. It's like the call doesn't look correct to me. Is there any documentation that says that the opcode is invalid? There's got to. Oh, I know what we can do. We can use the online disassembler, which is also very cool. Start disassembling. It also has the ability to assemble. If you guys have never used this thing, you should check it out. It's pretty cool. Let's go to enter. Okay, so what was the opcodes that we were looking at here? 48CB. So rexw.retf. I'm wondering if, like, we just get rid of that. Should we just give that a go? Just CB. I'm thinking we should. Oops. While we're at it, I will ditch this breakpoint here because we don't need it anymore. And actually, instead, I will put it here so that we can break. Oh, we've hit another null pointer or something similar. There we go. Right, so retf. Is this going to be any different? I'm going to go with no. Ooh! Haha! See that? We're in 32-bit mode now, I hope. Red Dragon, peace. Peace, my friend. So the stack points to just above, so it's pointing up here, which is perfect. And it's 32-bit aligned, which is great. So what happens now? We get a seg fault. So what I'm going to do is I'm just going to get rid of this for a minute. And I'm also going to get rid of this. See what it does. So it's definitely seg folding at that point. Now, what a nice ride down memory lane, yeah. So true. So what I'm going to do here is I'm actually going to not attach. I'm just going to see what it does. Clearly nothing. How do we check? Oh, we need to check the value of the CX register. Yeah. Clearly we had them the right way around, didn't we? Otherwise we wouldn't have landed back in the spot that we were expecting to. Actually, I'll leave that one like that, but I'll still keep this out. So when we step in here,
Pattern recognition.
this is definitely functioning the way I would expect.
Altered patterns. Musician creates the pattern and makes us anticipate a resolution and holds back.
Ah, yes. Yes, yes, yes. This is interesting. You know what I'm going to do? Rather than use... Actually, I think it might be a little bit late for doing what I was about to suggest. Rather than use the execv bin sh shellcode from here, maybe we should just use one of the ones that we know exists out on the internets. x86 execv bin sh shellcode. There's like a 30-something byte, 23 byte. Is it this one? I've tried this 23 byte one a number of times, and I think it fails, whereas this one here doesn't. Now I can't see any dodgy shellcode in here as far as bytes are concerned. Oops. So let's do this. Now, the problem we've got here is the one in Ponytails is good. Oh, is it? Ah, fucking sweet. Sweet. Okay, so let's do this then. We'll call this execve equals. So I'm guessing pwn.shellcraft. I don't like to import star from pwn. I usually reference it by name. .i386 .linux .exec de. I'm going to go bin sh instead of /bash. Ooh, I'm doing something wrong. I say so execve. Do I need to... Is this right? Because it looks like you had an extra parenthesis in there somewhere. x86. Is it like that? Yeah. So then what I might do here is go... Just to keep things the same. This is blatantly cheating. Yeah, it's the code though. Yep. So here I'm going to go right, cool. Like this. Yeah, like that. Oop. Pwn.asm execve. Thanks, Sin. Still really helpful, man. I very much appreciate that. So buff needs to be whatever execve is padded L just 2. I'm just going to fill it out with, again, breakpoints. The length of what buff is. Now this is me being super lazy because this is what, 82 characters or something, and this is probably going to be really small. So I'm just basically saying justify this block so that it's the same size as this original one, which means all of the offsets that I've got stashed in here that I've hard coded, I don't need to go ahead and muck with. That's me being super lazy. Feel free to sue me. args are just around the other way. Yes, you're right, Ash. Thank you. Is it L just or L pad? No, that's right. No, that's definitely right. Oh, I'm looking at the wrong one. Sorry. Yep, my bad. There we go. That's better. Thank you. Okay, let's see how we go here. That's looking good. That's looking good too. I don't think there's anything wrong with that. Ooh, look at that. New program, user bin bash. Programs, oh, look at this. Bad system call. That's pretty funny. I wonder if that's got something to do with it failing to return sort of back into 32-bit mode or something similar. Let's see. No, still not happy, is it? Stopped with exit code SIGSYS. Do I need to do anything else magical? Oh, hang on a second. No, I am barking up the wrong tree. You guys got any ideas? What could I be missing here? What could I be missing? No one got any ideas? I would have thought that should have worked. What am I doing wrong? Any ideas, boys, girls? No? It's dying in the 32-bit execv syscall. Well, I don't know if that's true. So if we reattach. Look at this. Process is executing new program. So it looks like it is actually doing it. But then immediately after that, we get this program terminated with bad system call. Why would that be? Does the child process inherit its seccomp flags? Ah, okay, so remember how in the original challenge it said, let's go back over here. You can use bash. It's as if this is custom. Do all the built-in shells try and like change privs? You know what I mean? Because if they do, maybe the seccomp filters don't get passed down, but the other filters do. SH doesn't drop, I think bash does. Yeah, but I think in this case, SH is an alias for bash. Right? So, let's just go over here for a minute. Yeah, so that's just a symlink to bash. What else could we install? Is there a shell out there that doesn't attempt to drop privs that's in here by default? Does the error message indicate that bash is dying when it tries to syscall read from standard in? Did the error message indicate the bash is dying when it tries to syscall read from standard in? Let's go back to that for a minute. So this says here bad system call. Shouldn't it be bin bash bin sh? Yes, it should, and that's exactly what I'm doing here. But if you go ls-la of bin sh, you see it links. It's just symlinks to bash. So on this operating system, that's what it does. So the question is, yeah, that's pretty savage. Hey, is there some way of getting a shell? Because I'm wondering if, because remember we had two process control calls, yeah? The strace the whole lot following children, would that show you what's dying in what? Hey, it's Buster B. Nice to see you, man. The challenge had a custom bash binary so you could call it. So yeah, you need a 32-bit binary. Ah. Yes, that's probably fair. You need a 32-bit bash. Is there a way of nicely installing a 32-bit bash without screwing everything up? That's an interesting question. Anyway, what I was going to say was, come on, back over here in at seccomp. Remember we had, oh crap, we had two calls, and the first one turned off. Which one was it? It was something to do with the privileges. Sorry, I'm a bit all over the place. Where is it? That's right, no new privs. That's what we were dropping, yeah? No new privs. Promises not to grant privileges to do anything that could not have been done. Once this set can't be unset, the setting of this bit is inherited by children created by fork, clone, and preserved across execve. Yep, okay. So this is the thing that might well be killing us. Does it? I don't think it really needs to be a 32-bit binary for this to work. I'm pretty sure. I reckon it's just the privilege drop that's the problem. Or the privilege change, that's the problem. No new privs. So we need basically something that's an interactive shell. So I know this machine here is, let's go Fedora install sh. No, not. Dash, does dash do the same? Let's see if we can install dash. Have any other random shell? I got ZSH. There's no KSH. I checked for corn shell before. Let's see what happens. You could just use 32-bit interpreter. Well, actually, yeah, I probably could do that. But I'd like to just have a standard shell and reuse the existing thing. Okay, let's see. Now the problem is Vim. It's so tempting. So tempting. We're so close though, hey, we're so close. Problem that I've got here is, oh no, we've got this, don't we? It's user bin dash. User bin dash. Bad syscall. I thought dash was a fairly up-to-date replacement for a bunch of others that also did the privilege drop. Am I wrong? It's definitely invoking it, clearly. I got an idea. Let's do this. See, this is pretty elite stuff. GCC M32 main dash O. Okay, so hi. Pretty lame, huh? So instead, I'm gonna go home OJ stream diary winning. Okay, look at that. We didn't actually get anything bad. Hi, we got hi. Subs a PR for highway. Yeah. Okay, so the question is, like clearly I've just cheated by creating a 30. I don't think it even needs to be 32-bit. So what I'm going to do is just, I'm going to do that GCC again. Let's get rid of M32. And I'm going to do the same thing. Ah, yes, it does need to be 32-bit because the 64-bit version is killing it. Who said that? Somebody said that already, didn't they? We do need a 32-bit shell. So, hang on, I'm going through the backlog. Somebody said it. Sin on YouTube said, so yeah, you need a 32-bit binary. And you are damn right. Of course you're damn right. Because we're still within the same process. And the seccomp applies to 64-bit. So if we invoke a 64-bit binary, we're going to end up back in a land where we can't use that stuff. So, ooh, Buster B is sending magic links. What is this? libsteven shell. Yes, that's what I want. Let's grab that. Ooh, no, that's not what I want. I want the rm main.c.1. We need the raw version, don't we? We need the raw version. What is the raw version? So I'm just grabbing a link. I should open this up in the browser so you guys can see. This is what the legendary Buster B, Brent Cook, has sent us. So we need the raw version of the Stephen Brennan shell. Let's take that. W get that. Let's just move that to main.c. Please work. Haha, here we go. All right. Exploit, we're still pointing at winning. Are we gonna win? You know what, I'm gonna remove the breakpoints. Oh, we don't have any breakpoints. Hooray. Okay, let's get rid of the attach. Oh, and? No, No, why? It didn't break though, did it? I wonder why that didn't work. Any ideas? Maybe it's 64-bit. Maybe LS is 64-bit. Yeah, that's a good point. Maybe all of those things are 64-bit. Are they all behind the scenes? Turn it off and turn it back on. So look, I think it's fair to say at this point that we're definitely locked in a realm where we can't do 64-bit syscalls, and everything behind the scenes, even outside of our payload, is 64-bit. But I think, given the nature of the challenge that we've addressed, that we've taken on, according to this bash thing here appears to have been a 32-bit version that allows you to do maybe more. I haven't read the write-up, so I don't really know. I think we can probably call that a win. Do you guys agree? Are we at a point where we can say, you know, we've done what we're looking to do and we can basically wrap things up? What do you all think? No, I'm not talking to you, Lekka. Do it all again. Love doing all this again. I think they just dropped the challenge in it. Yeah, that's exactly what I think. So you probably end up kicking off a custom bash that they have deployed, which does nothing but 32-bit shenanigans directly, or maybe has a very limited set of features. But yeah, maybe from there, like you had to, I don't know, do another step. But you know, we've demonstrated that we've managed to flip over to 32-bit land. I mean, from there you can go as far as you want, right? We could allocate a massive amount of memory somewhere on the heap and read an entire shell in, and away we go. So, did anyone else just hear I say, no, I don't want anything? First type I've seen Heaven's Gate-ish technique on. Yeah, I've not actually seen that either. Not on Linux, obviously. Windows Heaven's Gate related stuff I'm pretty down with, but I've never seen anything like this on Linux before. So it's very interesting to know that when you flick architectures, seccomp no longer applies. But yeah, really, really interesting. Thanks, Atwolf. We collectively did. We had some fantastic groupthink going on here. Some awesome gems from various people. I think Sin gets a special mention for dropping the seccomp tools in there. That was really, really good. What's different on Windows, as far as transitioning from one bitness to the other in Windows, is exactly the same thing, Smash. The only difference is what you can do from there. So I guess maybe to give you a bit more of a thorough answer is, in Windows, when you run 32-bit on a 64-bit system, you're running in WoW 64, right? Windows on Windows 64-bit, even though you're running 32. From there, as soon as you transition from 32 into 64-bit land, you actually don't have all of the libraries that you're usually relying on being loaded. So you end up with something like you got wow.dll and wow64.dll or wow64cpu.dll, but nothing like user32 or anything like that. So you end up with a very limited environment. Thankfully, in 64-bit land, when you're running under wow64, you can still call create remote thread, which allows you to inject into 64-bit processes. But strangely enough, in the other direction, when you're going from 64 to 32-bit, you have everything available. Go figure. So as far as the transition from 32 to 64-bit, it's exactly the same. But what you can do on either side of that, I think, is where the differences really lie. Does that answer your question? Sin, it's actually under pitfalls in Linux kernel documentation. Oh, okay, right. I should go and have a read about that then, because that's not something that I am familiar with. Swappage, you throw an idea about why something I'm trying to do in exploit writing isn't working, which is why I was expected. Yeah, cool. So for full disclosure, there was one point where what I really wanted to do was, okay, I had this problem. We're in Meterpreter. we're running 32-bit. We're on a 64-bit machine, which means we're in WoW 64. And what I want to be able to do is things like hash dump or run Mimikatz or something like that without actually having to migrate to a 64-bit process in order to do that, right? So I thought, what would be really cool is if I could create a command in Meterpreter called switch arch. And if you could do that, then you'd be in 32-bit mode. You can say switch arch and it flicks over to 64-bit mode. And then you could talk to Meterpreter as a 64-bit instance while still running in a 32-bit application. I thought that'd be really handy. So I started going down the path of implementing this feature using the heavens gates and blah, blah, blah to flick into 64-bit. And then from there, do what we would normally do as far as our reflective DLL injection process is concerned and load a new version of MetServe, which is a 64-bit DLL, into memory and kick off Meterpreter fully on its own thread under 64-bit despite running under WoW 64. The problem is that as soon as you flick into 64-bit land, all the shit that you need to rely on as a 64-bit process on Windows doesn't exist. So your DLLs basically shit themselves. I reached out to Scape, the famous Scape, Matt Miller, who works at Microsoft, who I've never met in person, but is an extraordinarily nice and very wickedly smart dude and was the father of the original Meterpreter implementation. And I asked him about this and said, you know, is it possible and is it worth pursuing? And his response was, technically it's probably possible, but you would have to do that much wizardry on a per Windows version process, abusing features that are really brittle and most likely to change across patch levels, that the sheer volume of maintenance required to make this feature work may not be worthwhile. And so, you know, I thanked him gratefully for that information, because that saved me a lot of pain. So unfortunately, switching architecture in that way wasn't going to work. Bummer, hey. So there we go. Look, I think it's fair to say we can call it a night there, and I reckon from there, if we had been doing this during the assessment, during the CTF, I should say, assessment. God, I sound like a pen tester. If we were doing this during the CTF, then we could have invoked that bash, and from there, hopefully, would have sniffed a flag out. So, yep, Swappage, what's up, mate? Fire your question at me. And anyone else, if there's anything else that I can add. x86 app exploited on Win64. Yep. Thanks, Brent. I appreciate you coming along as always, buddy. Syscall 02. What's Syscall 02 in 32-bit land? Can anyone remember? Is it a read? Crashes with access violation at blah. x86 syscall table. It's an egg hunting routine. Really? Can you tell me what government department's access points are so open? No. No, I can't. Back. Okay, look, here we go. This is a really good thing. Okay, so sysfork. Okay, so you're doing a fork. It crashes with an access violation. Check call and okay. Oh, so it's a Windows thing. Okay, now I'm confused. It's a Windows thing, but you talked about syscall 02. I'm a little bit confused as to why you're referring to syscall 02 on Windows. Sorry, mate, because you don't actually do direct syscalls on Windows, yeah? Thanks, Lurker. Appreciate it, dude. Thanks for coming along as always, mate. Your support is greatly appreciated. Yeah, so I'm not sure what you're getting at there, buddy. You might have to give me a little bit more information. Maybe do hit me up via email or something like that, and I'll see if I can help you out. But yeah, syscalls on Windows don't make sense to me. Anyway, look, I'm going to call a halt there. Thank you very much to everybody who came along, tagged along, enjoyed the show. Many more thanks to those people who offered insights, advice, and found bugs in my stuff as I was writing it, all of that kind of thing. And you know, by the looks of it, this whole broadcasting across Twitch, Mixer, and YouTube seemed to go quite well. You know, there were a few people on each platform, and I didn't have too many complaints. So with a bit of luck, everyone was able to see and hear all the things. I will make plans to adjust the way the chat window works so that you guys can get a better view. But you know, I'm really super grateful that you all came along and stuck through with me. It was really enjoyable. So thanks so much for that, guys. I appreciate it. And yeah, slick. So the chat that's appearing on screen is funneled from the 3 different platforms. So I'll probably end up making that a little bit more visible and keeping the comments appear or have the comments appear for a little bit longer before they fade away. So thanks Nemo, Swappage, Slick, Manuel or Manuel, sorry, depending on how you pronounce your name. At Wolf, same story there, man. That'd be awesome. I will look into other options as far as, you know, chats and things are concerned across all the platforms as well. So thanks Smash, I really appreciate that, dude. More things to learn as always. Same for me, man. Same for me. But yeah, I'll see you all on the twits and the tubes, and all the best and peace.